It lets us peek behind the curtain. So, in that first image, we were already looking at galaxies that existed over 13 billion years ago. Just a few 100 million years after the Big Bang. That alone was impressive. But here's the part that caught everyone off guard. Some of those galaxies looked too bright, too structured, too evolved. And that didn't line up. According to most models, galaxies back then were supposed to be small, chaotic, and still forming their first stars. But what Webb showed, even in that first photo, was something that looked much further along. Smooth structures, defined clusters, evidence of star formation that should have taken hundreds of millions of years more than the universe had given them at that point. So naturally, the questions started piling up. Were these galaxies forming faster than we thought possible? Were our models of the early universe just wrong? Or were we looking at something else entirely, a different kind of structure, built under different rules? And this was just day one. Before Webb had even locked in its full calibration, before its instruments had been tested across the board, it had already sent us back to the drawing board. Not because the data was unclear, but because it was too clear. It didn't confirm our expectations. It challenged them. What's wild is that this wasn't some deep survey that took months to complete. It was a snapshot, a glimpse, proof that even in the blankest parts of the sky, there are entire universes hidden in the dark, waiting, quiet, until the right lens came along. That lens was James Webb, and in just a few hours it rewrote our map of the early cosmos. A telescope like Webb wasn't built just to stare into the ancient past. It was also designed to look closer, not at galaxies billions of light years away, but at stars just down the street, orbiting their own little worlds. Worlds we've been chasing for years, guessing their shapes, estimating their temperatures, watching their shadows. And up until now, that's all we really had. Shadows. When a planet passed in front of its star, we'd see a tiny dip in light. That's how we found them. That's how we measured them. It worked, but it was limited. You can learn a lot from a silhouette, but it doesn't tell you what the planet is. It doesn't tell you what it's made of, or what's in its sky, or if anything's living there. Webb changed that. Its infrared sensitivity made it possible, for the first time, to read the actual chemical fingerprints of an exoplanet's atmosphere. Not indirectly, not through noise and modeling, but directly, by splitting the light that passed through it and analysing the spectrum, one wavelength at a time. That's how we got the first clear detection of carbon dioxide on a planet outside our solar system, WASP 39b, a hot gas giant 700 light years away. That one single result proved the concept. It wasn't just hype. Webb could read alien atmospheres. And then it went further. Webb found water vapor on WASP 18b, WASP 80b, and GJ 486b. These aren't friendly planets. One's boiling. One's practically hugging its star. But the point isn't that they could host life. The point is that we could read them, measure the thickness of their clouds, track changes in pressure, see signs of things like methane and sulfur dioxide, gases that mean something when they show up in the right combinations. Then came WASP 17b, and that's where it got weird. Webb didn't just find vapor or gas, it found solid particles in the planet's sky. Tiny silicate crystals, essentially glass, suspended in the atmosphere. The same way Earth's clouds can carry water droplets, this planet was flinging microscopic quartz around like hail. It was the first time we'd seen anything like that. And it made us realise something. Exoplanets don't follow Earth's playbook. Their weather systems, their skies, their entire logic might be different. Wildly different. And Webb was the first tool that could actually show us. But it didn't stop with exoplanets. Webb turned its gaze inward too, toward our own solar system. And even though these were closer targets, it still managed to surprise us. It captured the sharpest view of Neptune in over 30 years. Not just the rings, but the thermal profile, the pole, the cloud tops. The level of detail was unreal. Then it locked onto Charon, a strange asteroid with its own tiny ring system, and detected water ice. That's an object only a few hundred kilometers wide, yet Webb could map its surface. Then it turned to Europa, one of Jupiter's moons, and detected plumes of water vapor venting into space. That confirmed what we suspected from older missions like Galileo and Hubble. But this time it was crystal clear. Europa wasn't just frozen. It was active, breathing, jetting out the contents of its subsurface ocean like a leaky faucet. And Webb was watching it happen in real time. Even Comet 238P/Reed, a small rock in the asteroid belt, got its spot. Webb detected water, but no carbon dioxide, which was weird. Most comets have both. This one didn't. That tells us that maybe this comet formed in a warmer region than we thought, or that its CO2 has long since escaped. Either way, that's a clue about comet formation, about solar system chemistry, about how water made its way here in the first place. And then there were the trans-Neptunian objects, icy bodies way out past Pluto. Webb started picking up traces of methanol and organic compounds on them too, helping us piece together what the outer solar system was like in its earliest days. These weren't just static leftovers. They had chemistry, change, history. So yes, James Webb was built to look far, but it turned out to be just as powerful when it looked near. Because every time it focused on something we thought we understood, whether it was a planet we'd already discovered or a moon we'd been circling for decades, it showed us something we missed. In 2023, JWST started pouring in data from deep field surveys. One of the first things astronomers noticed was the sheer number of galaxies it was picking up in the first few 100 million years after the Big Bang. Not just faint blobs of light, not background noise. Fully formed galaxies, dozens, then hundreds, in places we thought were still empty space. And some of them were just wrong. Take CEERS 93316, for example. Based on its redshift, it looked like this galaxy existed just 235 million years after the Big Bang, the farthest galaxy ever observed at that point. That's way earlier than we expected anything that complex to exist, and it wasn't alone. Webb kept picking up more bright, compact, well-structured galaxies that didn't look like they were still forming, they looked done. And that was a problem, because to make a galaxy like that, you need time. You need heavy elements, you need stars that live and die and explode, and recycle their guts into the next generation. You need dust and gas and rotation and gravity, all working in sync over hundreds of millions of years. But these galaxies didn't have that kind of time. So, something wasn't adding up. Were these galaxies somehow forming faster than anything we'd ever seen? Were they forming differently, skipping steps we thought were necessary? Or was our whole timeline for the early universe off by a wide margin? And then Webb found something even stranger. The JWST Advanced Deep Extragalactic Survey, JADES, one of its largest deep field imaging programs, focusing on the GOODS S and GOODS N fields, offered detailed images of galaxies at high redshifts. These observations were expected to refine our understanding of galaxy formation and clarify how supermassive black holes achieved their enormous masses so early in cosmic history. However, a surprising discovery from JD's data has challenged fundamental assumptions about the universe's structure, specifically the principle of isotropy, which posits that the universe should appear roughly the same in all directions, with no preferred orientation or spin. In a study led by Leo Shamir of Kansas State University, researchers analyzed 263 spiral galaxies in the GOODS South Field using the Ganalizer algorithm, which assesses galaxy spin direction from radial intensity points. The results revealed a striking asymmetry. 158 galaxies, 60%, rotated clockwise, while 105, 40%, rotated counterclockwise. This imbalance hints at a possible preferred spin direction in this region of space, challenging the notion of a directionless, homogeneous universe. Previous studies have noted similar spin asymmetries, with the effect appearing more pronounced at higher redshifts, suggesting a potential primordial structure in the cosmos. Some speculate this could align with physicist Nikodem Popławski's unconventional theory, which proposes our universe formed inside a rotating black hole in a parent universe, possibly imparting a directional spin bias to cosmic structures. However, Shamir's team offers a more conventional explanation. The asymmetry might stem from a Doppler effect bias. The Milky Way's motion could make galaxies spinning opposite to our perspective, clockwise from Earth, appear slightly brighter due to blue shift, potentially skewing automated classifications. The small sample size of 263 galaxies and the challenges of imaging faint high redshift objects further urge caution. Larger, more diverse datasets from ongoing JWST observations will be crucial to determine whether this asymmetry reflects a true cosmic phenomenon or an observational artifact. Compounding these challenges to cosmological models, JADES has also uncovered galaxies with redshifts exceeding 13, meaning they existed when the universe was less than 330 million years old. These galaxies, far from being weak protostructures, are luminous, compact, and surprisingly mature. A standout example, JADES GSZ 13-0, with its extreme redshift, has forced astronomers to reconsider how early galaxies could collapse from primordial gas clouds in such a short time frame. Typically, such collapses require extended periods, yet these galaxies appear fully formed within the universe's first 300 million years. This is not an isolated anomaly, but part of a pattern. These early galaxies weren't just existing, they were thriving, actively forming stars at ridiculous rates. More stars than they should have been able to form with the limited ingredients available. It was like watching a campfire suddenly erupt into a 5-alarm blaze, but in the vacuum of space, before the wood had even dried. Some astronomers started calling it the too early, too big problem. The galaxies were too massive, too luminous, too soon. So, what's going on? One possibility is that star formation in the early universe was simply more efficient than we thought. Maybe conditions back then, higher densities, more frequent collisions, allowed galaxies to grow at warp speed. Or maybe our models are missing some critical ingredient, a cooling mechanism, gravitational effect, something we haven't accounted for yet. Another idea is that these galaxies formed from direct collapse. Instead of slowly gathering stars and building up mass, maybe some of them collapsed almost instantly from dense gas clouds, forming stars and black holes in one quick chaotic event. If that's true, it could explain how some of the earliest quasars, the super bright beacons powered by black holes, came to exist so early too. But here's the twist. The more we try to explain it, the more complicated it gets. Because every time Webb stares into those early epochs, it finds more galaxies, not fewer, more light, not less, more structure when we expected randomness. And now, astronomers are facing a deeper question. What if the early universe was never as quiet as we thought? What if everything, stars, galaxies, black holes, came online faster and louder than we've ever imagined? If that's true, then the universe isn't just older than we thought. It's busier, more aggressive, more alive, even in its infancy. And all of these findings that broke our timeline, they came from just the first year of Webb's deep field work. We're only scratching the surface. The moment we found galaxies that were too big for their age, another question came up right behind it. If these galaxies are already so massive this early, where are the black holes that should have grown with them? That's been a long-standing puzzle in astronomy. We know most large galaxies today have a supermassive black hole at the center, sometimes billions of times heavier than our sun. But we still don't know exactly how they form. Do they start as small ones that slowly eat their way up? Or do some just appear fully grown? James Webb didn't solve that question, but it gave us something we didn't expect, proof that these monsters were already around in the early universe. One of the biggest surprises came from a galaxy called CEERS 1019. It's distant, faint, but when Webb looked closer, it saw a clear signal, the telltale signature of an active galactic nucleus, meaning there's a black hole in the center and it's feeding, not just existing, not just waiting, feeding. That's important because CEERS 1019 isn't in the modern universe. It's from a time when the cosmos was only about 570 million years old. So, how did a black hole, even a small one, form, grow, and start actively pulling in matter that early? That's not supposed to happen. Black holes need material. They need mass to form. They need stars to die. They need galaxies to evolve. And all of that takes time. But this one, and a few others like it, seem to skip that timeline entirely. They're just there. That led researchers to revisit the controversial idea, direct collapse black holes. The idea is that instead of forming from stars, some black holes might form straight from massive clouds of gas, collapsing under their own weight before a single star ever shines. It's messy, it's fast, but it might explain how black holes could have been born big. And once they're big, they don't stay quiet. That's where quasars come in. Webb began spotting quasars, incredibly bright beacons powered by black holes gobbling up matter, from more than 13 billion light-years away. One of them, in a galaxy called J0439 plus 1634, had light so distorted and amplified that it could only be explained by gravitational lensing, a giant galaxy cluster bending the path of its light across space. That's not just a pretty trick, it's a window into the deep past. Lensing takes objects that would normally be too faint and stretches them out, magnifies them, gives us access to more detail than we should be able to get, and it works both ways. One of the most striking examples came in September 2023, when astronomers spotted a supernova, a dying star, that had been triply lensed by a galaxy cluster. It was nicknamed SNH0P. It appeared in 3 places at once, all slightly offset in time. Think of it like a cosmic time delay, the same explosion playing back through different routes in space. That's more than just fascinating, it's useful. By measuring how long each image takes to appear, astronomers can actually use lensed supernovae to measure the expansion rate of the universe, something we've been arguing about for years. There's a whole debate called the Hubble tension, the idea that our 2 best ways of measuring the universe's expansion rate give different answers. But lensed supernovae like SNH0P, they offer a third way, and Webb's sensitivity makes it possible to catch them early, even when they're faint. So, while it's out there spotting galaxies and black holes that shouldn't exist yet, it's also quietly helping to solve, or complicate, one of the biggest cosmological arguments we have. But then Webb found something even stranger. It started seeing galaxies that were no longer forming stars, not millions of years into the universe's history, but within the first billion years. These weren't galaxies that were just starting to wake up. They were already quiet, done, as if they'd been lit up briefly, burned fast, and then just stopped. That's not supposed to happen either. Galaxies are expected to go through a long, messy adolescence. Stars forming, dust flying, chaos all around. But these galaxies, found just 700 million years after the Big Bang, were already quiescent. That's the technical term. No new stars forming, no gas left to work with. It's like finding an elderly person in a kindergarten classroom. You don't expect to see someone that evolved that early. But Webb found them, multiple times. They're now being called Sleeping Beauty galaxies. Catchy name, strange reality, because we still don't know why they stop so early, or if they might wake up again. But it's clear that star formation, just like galaxy growth and black hole birth, doesn't follow one simple rulebook. For a while, Webb's discoveries were all about what we didn't expect. Galaxies too soon, black holes too big, stars forming too fast. But in early 2025, something changed. The conversation shifted from structure and timing to life. The target was K2-18b, a planet about 120 light-years away, orbiting a cool dwarf star in the constellation Leo. We'd known about it for a few years. Other telescopes had picked up hints that it might have water vapor in its atmosphere. That alone made it interesting. Not Earth-like, but still in what's loosely called the habitable zone. Not too hot, not too cold, just maybe right. But Webb saw something more. In April 2025, scientists announced they had detected dimethyl sulfide, or DMS, in the planet's atmosphere. On Earth, this molecule is only produced by life, specifically by marine plankton. No volcanoes, no lightning, no chemistry we know of makes it without biology. However, scientists caution that unknown abiotic processes, e.g. photochemical reactions in hydrogen-rich atmospheres, could potentially produce DMS. Now, it's important to be cautious here. This isn't confirmation of aliens. It's not proof of anything. The signal isn't strong enough yet to be called a detection beyond all doubt. But the odds? They're high enough to pay attention. Some estimates put the confidence around 99.7%. Not certainty, but not noise either. Webb didn't just pick up DMS. It also spotted methane, carbon dioxide, and hints of dimethyl disulfide. All molecules that in the right mix could point toward biological processes. And K2-18b isn't a gas giant. It's what we call a Hycean world, somewhere between a super-Earth and a mini-Neptune. A water-rich planet with a thick atmosphere, possibly with a global ocean under clouds. That combination, water, methane, CO2, and DMS, is strange. Not impossible in theory, but very unlikely without something living in the mix. Of course, people debated. They still are. Could photochemistry do this? Could there be some exotic process we don't understand yet? Possibly. But that's what makes the observation important. It raises a real testable question. And it's the first time we've ever had that from a planet outside our solar system. No artist's impression, no theory, just data. And while the headlines ran with it, sign of life? The real value is quieter. Webb is finally giving us what we need. Clues, not stories. Signals, not speculation. But that wasn't the only milestone Webb crossed. In May 2025, astronomers confirmed the detection of the most distant galaxy ever seen. A compact, bright object named MOM-Z14. Its redshift was calculated at Z approximately 14.44, meaning the light left it over 13.5 billion years ago, when the universe was just 280 million years old. Let that sink in. We're now looking at galaxies that existed when the cosmos was less than 2% of its current age. MOM-Z14 isn't a massive system like the Milky Way. It's small, intense, bursting with star formation. But it's real, and it's not alone. Webb's deep fieldwork has identified dozens of similar candidates, slowly filling in the blanks of a time we've never truly seen before. Then came one of the strangest visual surprises in recent memory. In July 2025, the James Webb Space Telescope captured an extraordinary image of two galaxies caught mid-collision, forming a system dubbed the Infinity Galaxy. When processed and sharpened, the combined shape resembled a near-perfect infinity symbol, a figure-8 twist of stars, gas, and gravity. Astronomers were captivated by its striking appearance, but the real story lay deeper. Now, yes, the shape got attention, it's striking, but the real story wasn't the symbol, it was what was hiding inside. At the heart of the collision between the two galactic nuclei, researchers identified a supermassive black hole, actively feeding, pulling in material, and building mass. Based on its brightness, energy output, and the extreme gas density of the collision, there's a compelling possibility that this is a direct collapse black hole, a rare phenomenon where a massive gas cloud collapses directly into a black hole without forming stars. This could be a critical clue to one of astrophysics' biggest mysteries: how supermassive black holes grow from nothing to giants in a relatively short time. The Infinity Galaxy, observed about 7.5 billion years ago when the universe was roughly 6.3 billion years old, isn't from the earliest cosmic epochs, but it offers a vivid snapshot of the chaotic mergers that shape galaxies and their central black holes. More than a stunning image, it serves as a laboratory for studying the processes that drive the formation of the universe's most massive objects, illuminating how collisions and extreme environments can spark the rapid growth of black holes. We've been detecting exoplanets for nearly 3 decades now. And in all that time, we've mostly done it by inference, watching how starlight dims, shifts, or gets distorted by something passing in front of it. It's effective, but it's never really felt like seeing a planet. It's more like watching a shadow dance and trying to guess what cast it. So, when the James Webb Space Telescope captured its first direct image of an exoplanet, it wasn't just a milestone, it was a moment of clarity. It happened in September 2022. The planet, Ship 65426b, hadn't even been the focus of any headlines before. One of the quieter targets, orbiting a faint star about 350 light-years away. Not Earth-like, not habitable, just a massive gas giant, several times the mass of Jupiter. The kind of planet that's easier to image because it's big, bright in the infrared, and sits far enough from its star to not be drowned in glare. But that's exactly what made it the perfect test case. Using its coronagraph, a device designed to block out a star's blinding light, Webb was able to isolate the faint glow of the planet itself. Not a shadow, not a spectral trace. Actual light coming from the planet's atmosphere, captured and analyzed in detail. That light revealed temperature, cloud composition, molecular fingerprints. It confirmed methane, detected water vapor, even suggested deeper structures in the cloud layers, things like pressure systems and haze. And for the first time, scientists could study a planet in another solar system as a world with its own visible character, not just a line on a graph. Of course, this kind of direct imaging isn't new in theory. A few ground-based telescopes have managed to do it under very specific conditions. But those images were faint, noisy, barely enough to tell you what you were looking at. This one was different. This was clean, high resolution, detailed enough to break down what the atmosphere was doing, not just what it contained. It was the first time the distant glow of a world outside our solar system could be treated like real data, not a suggestion. And now that Webb has proven it can do that, the possibilities just open up. Planets like HR 8799c, Beta Pictoris b, and eventually the smaller, cooler ones, the ones we really want to understand, are now within reach. Slowly, carefully, but for the first time, visibly. And again, this wasn't hype. There was no big countdown, no splashy press event. The data was released through peer-reviewed studies, and the image, while simple, carried all the weight of 2 decades of engineering behind it. This is how major progress happens now. Quiet, technical, measured, but undeniable. And while Webb was doing that, it also turned its attention to things much closer, things flying through our own neighborhood. Like asteroid 2024 YR4. This was a near-Earth object about the size of a 15-story building. Not a headline grabber, not a threat, but still worth studying. The small, fast-moving asteroids are hard to observe with traditional telescopes. They move quickly, reflect very little light, and often slip past with only a brief window of visibility. But Webb caught it, tracked it, measured the surface composition, determined its exact orbital characteristics. It even helped refine the risk models for the Moon, which had a low probability impact window due to gravitational interactions. It wasn't flashy, but it mattered, because it showed that JWST isn't just good at looking into the past, it's good at looking around, at scanning the space near us with more detail than any telescope has ever had, even when the object is small, dim, and moving fast. And that's part of the real story. Everyone thinks of Webb as the deep universe machine, and it is. But its infrared sensitivity, precision tracking, and spectral resolution have made it useful for everything from icy moons to dusty comets to active asteroids and beyond. It's not a one-trick telescope, it's a toolbox. And the things it's helping answer, from atmospheric chemistry to orbital dynamics, aren't separate. They're connected. Because if we want to understand how common Earth-like worlds might be, or how life could survive in harsh conditions, or what early planets even looked like, we need all of it. Not just the distant galaxies, not just the biosignatures, but the full picture, from here to the edge of what we can see. By now, it's obvious that James Webb isn't just another space telescope. It's not a sequel to Hubble. It's not a mirror in the sky that happens to see a bit further. It's something else entirely. Something that's quietly reshaping how we understand the universe. Not by screaming headlines or dramatic discoveries, but by collecting the kind of data that changes everything over time. That change isn't always loud. Most of the time, it's just a shift in what questions we're even allowed to ask now. Before Webb, we had guesses about the early universe. Now we have measurements. Before Webb, we could detect an exoplanet. Now we can describe its weather. Before Webb, we thought galaxies took their time. Now we've seen them form, burn out, and fade, all within the first billion years. And that's the shift. Not just in what we know, but in how we think about what's possible. Because what this telescope has shown over and over is that the universe didn't evolve slowly and predictably. It evolved fast, and sometimes violently. Galaxies grew faster than we thought they could. Black holes didn't wait their turn. Stars formed, burned out, and passed the torch long before we were supposed to be able to see them. And yet, there they are, clear as day, sitting in Webb's data. So now we're left in an unusual place. A place where some of the biggest answers have raised even bigger questions. Why were so many galaxies already mature when they shouldn't have had time? How did black holes appear so early, or what made them feed so fast? What kind of worlds are out there that can carry not just water and clouds, but chemicals we've only ever seen here on Earth? And, maybe the most honest question of all, how much of our understanding was built on models that were just too neat, too slow, too simplified? Webb isn't here to confirm what we thought. It's here to challenge it, to test it, to make sure we're not just building stories that feel right, but ones that match what's actually out there. And it's still early. There are thousands of observations in the pipeline that haven't even been made public yet. Entire surveys that will run for years. Missions planned to pair Webb's results with new instruments, ones that'll look in other wavelengths or catch up in resolution. And then there are the things we haven't even imagined yet. The surprises, the quiet anomalies, the strange patterns in background galaxies, the leftover questions from redshift measurements that don't quite align, the weird atmospheres, the gaps in stellar mass, the lensed flashes that might be something more. Because the thing about a telescope like this is, you never really know what matters until you do. And when you finally do, it's never what you expect. No one knew Webb would find galaxies that shut down before they even got started. No one guessed we'd get hints of life from a planet 120 light years away this soon. No one expected such clear detail, from the furthest galaxy ever seen to the clouds on a gas giant right next door. But that's what it's doing. Not once, not occasionally, but constantly. And in doing that, Webb has quietly shifted astronomy from a field based on hopeful estimation to one grounded in evidence, detail, and sometimes uncomfortable clarity. It's not about pretty pictures. It's about finally seeing what's real. And if this is what the first 3 years look like, the next decade isn't just exciting, it's going to change everything.
Close your eyes and imagine yourself within a supervoid. Darkness envelops you, holding you captive and isolated. With your eyes, even with any amateur telescope, you see nothing. No stars, no hint of the fuzzy smudges we now know as our own neighboring galaxies. To you, the universe is empty. The Boötes Void is a spherical region 330 million light-years across, approximately 0.2% the diameter of the entire observable universe. The Milky Way could fit inside it millions of times over, and yet within a volume of about 1 million cubic megaparsecs, where there should be thousands of galaxies, we have observed only 60. Spiral galaxies, blue with the light of new star formation. To quote astronomer Greg Aldrin, if the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Indeed, were the Earth to rest on one edge of this void, observers on the other side would only now be receiving light from a time when amphibians dominated the Earth, before even the age of the dinosaurs. Even now, we do not fully understand how such a void came to be. The age of the universe sets a limit for the maximum size of any structure, galaxy clusters, and indeed the voids in between. There should be no single structure in the universe that is already greater than tens of millions of light-years across. The great nothing, as the void is known, shatters this limit. Though its absence of structure does give us an insight into the growth of structure at the earliest of times. A few galaxies observed within the void following a tube shape, perhaps the crumbled remnants of a wall between two voids. Individually, these voids would each fit within the growth limit, but together they form a supervoid. And so, even here, in the great nothing, one of the darkest places in the universe, there is the light of galaxies, unveiling their secrets to us through the visible spectrum. To find true darkness, we will have to look further than even the Boötes Void. Further back in time. We can only find complete oblivion in the time before stars and galaxies and planets existed, forebodingly known as the Cosmic Dark Ages. Here, the darkness was total and long-lived. Although for about 200 million years after the Big Bang, the universe contained a variety of ingredients that could produce the first stars, none formed. There was no visible light at all. But why was the cosmos dark for so long? What does this mean for the stars and galaxies we see around us today?
Fucking tired.